two Hilbert spaces. So we should try to generalize that or categorify it. So the way the Fock space works, it's what an algebraist would call the symmetric algebra, and it's what a high school student would call polynomials. So if you have a Hilbert space, you can form the algebra of the symmetric algebra on it, with a free commutative algebra on it, just by looking at its tensor powers and modding out by the action of the symmetric group. And then if you complete this, you get a Hilbert space. And so the idea is that if H is the space of possible states of a single particle, then this summand here is the Hilbert space of n particles of that kind, but n indistinguishable particles. So that's why we mod out by the symmetry. So it was discovered that electrons don't have names, that electrons don't have personal identity. So if I switch two electrons, there's no way for anybody to tell that I've done it. And so that's why we're modding out by this. If you know about bosons and fermions, then I guess I didn't pick the best example. I should have picked photons. But anyway, never mind.
This is for bosons, right?
Yeah. This is a bosonic Fock space. So my example of electrons, maybe I was hoping that there were no real physicists in the room, but yeah. Let's do bosons. Yeah. Now I found out. Yes. Yes?
Sorry, I missed one thing. At the beginning, you say that TQFT is a symmetric monoidal functor from NCOB to Hilb or NHilb. Okay, but
Hilb.
Okay, what is the tensor product in COB and NCOB?
It's disjoint union.
Just the disjoint union?
Yeah.
Okay.
So, right. So I can. So like if I'm doing 2 cob, I could. Every object is a disjoint union of circles. So Z of this thing would be Z of this thing. This is a circle. Tensor. So the monoidal functor is saying something like that. And then similarly for morphism. Sorry?
It's a little bit like smash product.
It's just disjoint union. So no smashing, just disjoint union. So no points getting identified. So the idea is that in quantum mechanics, when you have two separate physical systems, each of which has a Hilbert space, you say, what's the Hilbert space for the combined system? It's the tensor product. So here it's like, you can imagine a funny universe where there are two completely different disconnected parts of space. And then we should just form the tensor product. Yeah. So on Fock space, there's some very important operators. There's a creation operator. So if we, for example, pick a basis for our Hilbert space, then for every basis vector, since this is an algebra, you can form an operator where you multiply by that basis vector. So here's a typical example of a product of vectors in here. We just multiply it by one more. And that's called the creation operator. And the reason why is that we think of this vector in here as describing a situation where you have n different particles, one of type V1, one of type V2, and so on. And what this operator is doing is it's creating a new particle. It's just artificially putting in a new particle of type EI. And that actually, that's how physicists describe processes that involve creating particles. And then because, well, I wrote it as a dagger just because that's the traditional physics notation, but it's adjoint, which I guess I could write as AI dagger, but it's called AI, would be another operator. And that's called the annihilation operator, and that turns out to describe getting rid of a particle, destroying a particle. And Heisenberg didn't think about these things in quite this way, but he noticed there's a very physically useful algebra generated by the annihilation and creation operators, which obeys these sort of obvious relations. Because this is a commutative algebra, these creation operators, which are multiplying, commute with each other. This means this is the commutator. Sorry, the creation operators commute, therefore their annihilation operators commute. But they don't commute with each other when the indices are the same. They don't commute. Another way to think about these is that this operator is taking a polynomial and multiplying it by some variable. The annihilation operator just differentiates the polynomial with respect to that variable. And multiplication and differentiation don't commute when they both involve the same variable. So we get a non-commutative phenomenon here.